In this lesson, we're going to talk about the rules that govern image formation by flat mirrors. And in later lessons, we'll delve into convex and concave mirrors. But in this lesson, we'll introduce a number of important definitions that we'll use in these later lessons. So let's say we have a point source of light, a distance of p in front of a flat mirror. This distance p is called the object distance. And when light rays leave the source and are reflected from the mirror, if we trace these diverging rays backwards behind the mirror, they intersect at point I. Point I is the virtual image and is located at a distance of q behind the mirror. And we call this the image distance. So we got the object distance in front of the mirror and the image distance behind the mirror to the virtual image. And for flat mirrors, the image distance is always the same as the object distance. Another property of flat mirrors is the virtual image is the same size as the object. So for example, if we have a candle in front of a mirror and we trace out two rays of light from a single point on the candle, it could be anywhere on this candle, it doesn't matter. We only need two beams to locate the same point on the virtual image. And again, we do this by tracing back a line from the reflected ray. And of course, if we drew out an infinite number of beams from every point on our object here, on our candle, we'd find the exact location of the points in the virtual image. But what we find for flat mirrors is the lateral magnification of an image is equal to 1. Now, what does this mean? So we've got a formula here. The magnification is equal to the image height, so this is the virtual image behind the mirror, divided by the object height. So this is the height of our candle, for example. And when both these heights are the same, for example, if the candle was 10 centimeters high and its virtual image is equivalent to 10 centimeters high, then we have a lateral magnification of 1. And what you'll see in later lessons is that this lateral magnification will be different depending on the shape of the mirror. So let's try a quick problem. We have two flat mirrors perpendicular to one another, and an object is placed at point O. So in this situation, multiple virtual images are formed. Can you locate the position of all these images by tracing out rays of light from the object here? So how do we start solving this problem? All we need to find the virtual image is two light rays being traced out from a single point on our object. So I'm going to do this for mirror 1 first. So I'm tracing out two light rays going down towards the mirror, towards the left-hand side, and then reflecting up according to the law of reflection. And then I'm going to trace back these two lines, these two reflected rays, until they intersect. And where they intersect is where the first virtual image is located. Okay, let's do the same with mirror 2. So I'm tracing up two incident rays from our object to mirror 2, and they bounce off mirror 2 according to the law of reflection, where the angle of the incident ray is equal to the angle of the reflected ray. And these reflected rays, if I trace back a line until they intersect again, we get the second virtual image. But there's actually a third virtual image in this two mirror setup. If we draw out another two rays from our object that bounce off of mirror 1 towards mirror 2 and then bounce off mirror 2 again, then the reflected rays off of mirror 2, as I'm drawing here, if we trace back these lines until they intersect, we see a third virtual image, and that's our final virtual image in this setup. So in the next couple of lessons, we're going to talk about convex and concave mirrors and something called the focal point or the focal length.